Right, good morning everybody. Welcome to Kubernetes Network Security Demystified. My name's Andy, I'm a co-founder at ControlPlane. I've done a little bit of everything, broadly DevSecOps, but I think it's just engineering to the rest of us. And ControlPlane are a continuous delivery container security consultancy. So, what is network security and why do we need it? It's a way to ensure private, trusted communications across potentially untrusted networks with malicious actors, like the internet. And why do we need it? Because we can't trust anything. The internet was built for academics, with trust between all the workloads, and unlike those wonderful origins, we no longer can trust everything else by default. We think about runtimes, and we write software for the happy path, for the day boating on the lake, when in reality, there are pirates everywhere. We should be designing our systems for hostile conditions. Resilience is key. So, how does Kubernetes do this? It uses lots of standard components, but sometimes in a slightly different way to the internet. For example, self-signed certificates on the internet are considered bad, and are normally a sign that we have intercepted network communications, or potentially it's a man-in-the-middle attack. So we'll look at how Kubernetes uses encryption, establishes trust, and finally determines identity from the protocols that keeps Kubernetes secure and our workload safe. And if there's one takeaway from this, it is encrypt everything, everywhere. We're at the bleeding edge of a revolution that is already permeating traditional enterprise systems. These systems have high audits and compliance requirements, and breaking away from traditionally established network security patterns is difficult. There are many layers to a security onion, but the cloud-native landscape now gives us a problem and an opportunity. It's difficult to encrypt everything, and it's also difficult to encrypt workloads that constantly churn, as we expect containers to do, to die, to be rescheduled in other places. The SPIFFE project is looking to solve these issues for us. So this subject is broad and deep. We will scratch the surface of a few things, go into a little bit more detail in others, and hopefully leave you with enough hooks to go and explore the things that you find interesting. So we'll talk about network security 101, Kubernetes API components and their secure intercommunication, TLS X.509 and mutual authentication, the container network interface and network policies for applications, and finally, bootstrapping identity with SPIFFE, secure production identity framework for everybody. Without the framework, perhaps. So what do we want from network security? We want private and trusted communications. Private, very interesting. I wonder if that is the sign of things to come. Private means confidential, and trusted means with integrity. That is a network failure, I'm afraid, so I will just tether to my phone. Non-repudiation sometimes also makes an appearance here. All that really means is cryptographically we can prove that the person who sent the message cannot disprove that they sent the message, and this is relevant in courts often. Excuse me for one moment. We've got some network again. Okay, and things back later on. So normally, the slide we would expect here, voila, what a relief. So normally, let's just recap briefly. Yes, haha, the rise of the hackers, of course. Private, confidential, trusted with integrity and authentication. Non-repudiation we kind of don't care about, but it falls under the same banner. So, how does this look like from a human metaphorical perspective? Well, we can trust when someone's whispering to us that we know who they are, and we have privacy because the hand is protecting anyone from reading the lips or hearing the sounds. This is a bit like a private, air-gapped network. We believe there's nobody else there, so we take few or no additional steps to verify the integrity and the authenticity of the other party. This is okay in the smallest sliver of situations. It's not okay the rest of the time. If someone else sneaks into the room or is hanging from the eaves, then our privacy is broken. We need privacy and trust. So how does this work on bigger networks? Communicating over a public network is like shouting across a crowded street. We can see the speaker, or the IP, and we can hear their voice synchronized with the movement of their lips. But is this enough to trust somebody? Well, it kind of used to be. With the advent of all these deep learning generated fakes, perhaps we will need to apply cryptography to even the most mundane of video communications in the future. But again, this only works when both parties are local and have seen each other before to establish some sort of trust. What happens in life when we need to communicate remotely? We use the postal service. This, again, is analogous to the bigger internet. And the postal service question, do we trust when we send a message from one place to another that it arrives unopened and that it's from the original sender? Well, the UK has a long history of intercepting communications, steaming open envelopes, capturing the entirety of the internet traffic that transits out of the country. So, in order to get our privacy in the postal service, or indeed on the internet, we rely on encryption. And on the internet, that encryption is known as HTTP secure, or HTTPS, or TLS. And back we go in time to 1991. There were no certificates, and there was no GeoCities, but I thought it was a good opportunity to spark some nostalgia. We tried for a few years, and eventually SSL v1, it was no good, it was too difficult, it was broken. We had SSL version 2, more security flaws. Fundamentally, these are very difficult problems to solve. We went to SSL version 3, again, we see it's obsolete, and then TLS, transport layer security, replaced secure socket layer, but they're essentially the same thing with some small backwards incompatibilities. We moved through TLS 1.1, 1.2 is proliferated now, and we're just at the verge of getting 1.3 out of the door, despite some standards wranglings still going on. The only takeaway from this is cryptography is broken all the time with the advent of more computing power. We're about to move into post-quantum cryptographic algorithms, which have been investigated by parties in the TLS 1.3 spec. The only point here is keep your systems patched and up to date. Easier to do in containers than with hosts, immutable infrastructure is our friend, etc. So, is it that simple? Will Smith says, no. A single mistake anywhere in configuration, implementation, or usage can compromise the integrity of our encryption, leading to the oft-cited aphorism, don't roll your own. And there's no greater challenge for a cryptography nerd than an unhackable cipher, see Blu-ray. Cryptography is just a mathematical puzzle with some strict assumptions. And with that warning, on to Kubernetes. So, securing the API server. There are a lot of security flags on the API server. These are certificates, certificate authorities, and keys being configured. We're using TLS everywhere. How does TLS work? I'm glad you asked. We start with the certificate signing request, which details the identity that we want to be cryptographically signed and guaranteed. We pass it through to a certificate authority, who we trust either on the internet through a global trusted root store that our trusted operating system vendors put onto our machines and keep updated for us. And there's a revocation list, which means sometimes those certificate roots have been compromised or become untrusted, as Symantec has recently been from Chrome and soon from Mozilla as well. And then finally, we have the certificate. And when we have that certificate, we can guarantee that the certificate signing request data that is now in that certificate is legitimate via the certificate chain of trust. We start off with a certificate authority. Again, on the internet, these are the globally trusted root stores. We can also run these privately in our own PKI infrastructure, and this is what we're doing with Kubernetes. And everything we have here at each layer, from the certificate authority signing an intermediate certificate in case the intermediate is compromised, we can then rotate it easily by keeping the private element of the root certificate authority offline. And then finally, that signs the leaf, or end user cert. And that leaf is what we get when we go to a website, and that leaf is what we distribute, and that leaf contains our certificate signing request information. So, what are all these? They are X.509 certificates, which very simply is just a standard to define a certificate in this case. Okay, so we kind of have a broad TLS description. X.509 is the transport mechanism that we pass these around by, and we've also got mutual authentication. So we have a question now about how we bootstrap this authentication process, how we establish new encryption keys across a network that we don't trust, because initially we're bootstrapping the encryption. We're not already encrypted. So simply, asymmetric public key cryptography is a way to encode a secret using a public piece of information that the recipient, the target, has publicly shared, and we can use that to establish a shared secret, which we then use to encrypt the message in a way that only the recipient can decrypt it. So, very simply, the public key is available for everybody. These are the things presented by web servers when we go and visit them. And we use that public key to open up the metaphorical box containing our message. We insert the message that is private and only for the intended recipient, and then the box can only be opened by a separate key. And this is essentially public asymmetric encryption. There are a few bits of glossary that I'll go through very briefly here. Symmetric encryption, I mean, these are kind of maybe willfully ambiguous, but actually it's really simple. Symmetric encryption is just the same key used to do the encryption and the decryption. Obviously, this doesn't scale when we want to distribute the keys globally so that all clients can talk to our web server, cncf.io, etc. So asymmetric encryption is what we've just seen, using different keys either side of the encryption. Lock and unlock process. Then we have elliptic curve cryptography, which is the fundamental technique upon which these certificates, the mathematical technique upon which these certificates are based. And it basically means that when you plot this curve shape on a graph, and when certain guarantees are made, for example, the curve doesn't cross and loops around the plane, then we end up with something a bit like this, and we can essentially use the properties of this algorithm to generate the values which we use for encryption, and the point is they're very, very difficult to brute force. We won't go any further into elliptic curve cryptography because this is a lifetime study for the cryptographers who keep us safe. And the point here is that we finally end up with Diffie-Hellman, which is a way to create these shared encryption keys without ever communicating the key across a public untrusted network. And these gentlemen, Mr. Diffie and Hellman, are the heroes of cryptography since 1976. They fought with the US government. They were threatened for the export cipher. The US government put weapons-grade controls around these technologies, and these two guys really pioneered all the privacy and cryptography elements that help to keep us safe today. So, a brief whiz through that glossary and on to... Oh, and this is a really interesting cat-based description of the handshake in slightly more detail. I would recommend you check it out. So, we are now using the original crypto, not this shit. And on we go, back to Kubernetes land. So the API server is presenting a certificate. When kubectl wants to connect to the API, it goes into .kube-config, and normally what will happen in there, although there are many different authentication mechanisms, but with a self-signed certificate, the public key of the root CA, which in this case is Kubernetes, is embedded into the kube-config, and that's used to connect to the kube API server and trust that certificate. So we're back to this chain of trust. We have self-signed our own certificate authority, and when we come to communicate with the Kubernetes API server, we trust it because we have its public key. This is what would normally be distributed by our operating system vendors. In this case, we have our own version because Kubernetes is signing this for us. And what we actually have is a public key presented. We're back to the components. These are the things that make up the certificate signing request that go into the certificate. What does that certificate look like? Well, here is the spec. And how do we know that we can trust it? The certificate path validation that we've looked at earlier. This is an X.509 certificate. If you can guess what it is, you win a prize. And yeah, this lump of junk can be passed through standard command line tools like OpenSSL, and it will decode itself and tell you all the information inside it. It's really just containing, you could imagine it like it's just a tarball of information, although not literally. And there is a certificate that has been decoded. So we're back to these self-signed certificates, and we remember self-signed certificates on the internet are bad. We don't trust them. They could be the sign of a man-in-the-middle attack where somebody has intercepted our connection to a server. So it may seem that running our own certificate authorities is a bad idea, but when we're able to distribute the public key of our root CA, we can gain some advantages. For example, we can rotate those certificates very aggressively, and in fact, Istio has a default 1-hour rotation policy on those certificates. There is not enough global computing power to brute force a certificate in an hour. In fact, it's a lot longer because these are very difficult problems. So, so self-signed certificates can be used in, when we own the entire trust domain, not on the internet. So, we've mentioned this a couple of times already. The TLS Handshake, again, we won't go into too much detail, but this is just the client and the server saying, hi. The client asks the server, who are you? The server replies with its cryptographic identity. We have the privacy, we have the trust, because we can take the certificate back to our trusted root store, whether it's self-signed or public, and the client knows that the server is who they claim to be. Mutual TLS is the same thing, but the client also presents the certificate. So this means that we have two-way identity guarantees, and establishing a two-way trust mechanism is a good thing. We know the identity of both parties, and it enhances our baseline of security. So just to recap, we want private, confidential, encrypted communications. We're trusted, and we have integrity from the encryption, and the cipher guarantees that we get the correct output with the correct key. So, securing the API server traffic. Do we trust our networks? Well, frankly, no. And why should we? If a malicious actor gets inside the perimeter, they have access to everything behind it. Phrases such as perimeter and DMZ are old-school network security language that should raise flags in a cloud-native environment. So Google have a solution to this called Beyond Core, designed as a response to these newly emergent threats. This basically says, the mantra is trust nothing, validate everything, because the best way to bring pain forward and ensure that configurations are secure is to run everything publicly and revalidate every connection. This is called zero trust, and it contrasts deeply with traditional perimeter-based security, such as Equifax. In once, and then the entirety of the network is pivotable and approachable. So, this is all described in the book Zero Trust Networks by SPIFFE author Evan Gilman. If you want to understand the future of the way we're going to lock down workloads and applications over the next few years, this is a great starting point. But back to the API server. So, what does zero trust really mean in this context? Are we really running a zero trust API server? Well, not quite, but we're in the right direction. Zero trust here means that we mutually authenticate the TLS connection with client certs as the kube control config. It means we know the identity of the server and of the client, and we have our private and trusted criteria fulfilled. So zero trust is a lot more than this, but we're adhering to one of its basic principles, which is to restrict the blast radius of any potential compromise, i.e. some container or server has an unauthorized user and their intentions are malicious. So let's have a look at the API server components and their communication. I have Lucas Kallstrom to thank for this diagram, who is right now next door. And as we can see, a lot of things talk back to the API server, and all of these require encryption. They also all communicate via their own certificate authority, and we have different server and client certs for all the different intercommunications here. So, what would happen if we didn't do this? Well, how about some container has an unauthorized user? How likely is that? Well, what happens if somebody gets a remote code execution in a privileged container? Admit it, everybody is running privileged containers somewhere. So, we get into a privileged container, game over. Or, our user gets onto a load balancing box or something that's transiting packets to the API server, once more, game over. Or there's another container in the same pod as us that's compromised because, of course, we're all in the same network namespace, and if we have the appropriate permissions to sniff the traffic outbound from that other pod, well, you've guessed it. So defense in depth is our friend here. This is similar to how traditional breaches occur, a foot in the door, examining what else is available in terms of other network devices and pivoting and escalating privilege throughout the network until such time as we own the system. The attacker can gain a foothold through a seemingly innocuous chink and then pivot relentlessly. So we can fix this. For more on sealing up gaps in general with Kubernetes, I have another talk on continuous security, for which this cat is my favorite metaphor. And yes, these slides were published, and there's a link to those slides, which is too long to fit in with the cat. And it's a relentless focus on automation, allowing engineers to focus on the things that really matter. We do it once, we validate it, and we run it forever in our pipelines. So now that we think we are sure that the control plane is able to communicate in hostile waters, what about the applications running on it? For any application, the data store is the treasure trove. It's the value that any business inherently has, separate from their technology stack. This is why we back things up. This is why we can't lose data. But if we leak our database keys over the wire when our applications are trying to make connections, we may as well not have bothered encrypting the control plane. So what's next? Well, static endpoints are easy to encrypt because they have an IP, and we can use that IP as an anchor for the identity. And in fact, we can do the same thing with domain names. When we purchase a TLS certificate from a public vendor, the fact that we use a credit card is the trust mechanism. Just the fact that we are somehow in the global financial industry. So, what about dynamic resources? As we said, pods churn, they change all the time. Containers break the coupling between IP and identity. They churn, they get rescheduled, they're dynamic. So we need a component with a holistic view of everything in the system, everything in the cluster, rather, to run our firewalling for us. And our cloud-native firewalling is network policy. As you can see, the way packets move around Kubernetes is really very complex. There are multiple places that this could go wrong, so we use network policy on the CNI plugin, enforcing it at the container bridge to ETH level. Network policies are applied to pods by label. I hope everyone's seen this already. Labels, of course, the most innocuous but fundamental security primitive of Kubernetes because we address everything by label. With an empty pod selector, this network policy actually denies everything. It's a failed closed mechanism, which is probably the right decision, or I prefer to be more explicit, and we can't actually do so because this is illegal syntax. Here's another network policy that will only permit egress for port 53. Maintenance of policies is important as applications change, and it should be noted this is not for DNS-based, it's not for layer 7 traffic. This is for layer 3 and 4, where we are using the Kubernetes API to resolve the ports and IPs that our pods are communicating on with the labels that they're tagged with to resolve them back and reconcile them with a network policy. If we want, the reason for this is DNS lookups are fundamentally non-deterministic. They might be a DNS round robin, they might be a GeoIP based. There's no guarantee that what we get 1 minute is the same as what we get the next. And that makes things very difficult for Kubernetes. So the recommended pattern here is if we want to prevent egress to certain domains, then we should put a reverse proxy at the perimeter of our network and then use network policy to only allow specific pods to communicate with that proxy. So that's all very nice. This is illegal, of course, just to demonstrate. And as I said, these policies require maintenance. Of course, we wrote a tool for this. So this is a way of aggressively running Nmap in parallel from the same network namespace as a container. So what we do here is we define a deployment, a test front end, and running netassert in this case will SSH onto the node that one of those pods is running on. It will pull a container that it attaches to the same network namespace as that pod, and then aggressively parallelize Nmap to run in a near constant time for however many ports and services you want to maintain. This is really important because otherwise there's no way of knowing whether an application's required changes have broken some other part of our network security model. And it just gives you some nice tap output. So there are various other ways to do cloud-native firewalling. Some of these vendors are here. I recommend you go and talk to them. So we have got an equivalent firewall paradigm in Kubernetes now. What about our network encryption? Well, some container network interface plugins do support encryption, but it's a blanket encryption. So instead of using the identity of the caller and the sender, like TLS would do on the internet, to encrypt that communication and to use things like perfect forward secrecy to mean that even if that's all hoovered up, we're rotating the encryption keys very, very quickly. So breaking one bit of the communication does not break everything else. We just blanket encrypt everything. So a compromise of anywhere in the network means that we're essentially into the same encryption namespace in a way. Also, not all CNI plugins actually have any encryption, and thus, if we have no identity, then we have no authentication at this layer, and the public API is an attack surface. So we need something else to fix this problem. Enter SPIFFE. Probably heard a lot about this recently. SPIFFE has recently been accepted into the CNCF sandbox. And it's a set of open source standards for securely identifying software systems in dynamic and heterogeneous production environments. There's a reference implementation called SPIRE, and it's also implemented in Istio for some of the magical automatic mutual TLS. Concretely, SPIRE exposes the SPIFFE workload API, which can attest to software systems and issue SPIFFE IDs and SPIFFE verifiable identity documents, which again are just the X.509s that we know and love. This in turn allows two workloads to establish trust between each other using mutual TLS, and this will also, in the coming weeks and months, be extended for JOTs and web tokens and OAuth and all that good stuff, delegating third-party authentication. Very exciting times. So what do we have? We've got attestation policies, and this, for example, is where we get unique information about Kubernetes pod. An attestation policy describes the properties that a workload must exhibit in order to be assigned an identity, and are typically described as a mix of process attributes, such as a Linux user ID, and infrastructure attributes, such as running in a VM that has a particular EC2 label. And yet, in the Kubernetes workload plugin, the attester relies on the pod's endpoint of the Kubelet REST API and the information provided in proc PID C group. So SPIFFE is a standard for how an application can programmatically retrieve an identity for itself, and importantly, the short-lived credentials that go with that to assert its identity via a certificate signing request and that encrypted certificate document that we've seen from the internet at large. And more importantly, this also allows a trust bundle which can be used to identify other workloads. So that root CA, the public key of which we can use to identify other services. And by very finely segregating those stovepipes of application concerns, this severely limits the impacts of a breach. If one of those services suffers a remote code execution and an attacker is able to get into the pod, all that he can do is just what that pod is expected to be able to do with its pre-authorized mutual TLS neighbors. If he doesn't have a certificate to communicate with any of the other components, they will not even start the HTTP connection. The HTTPS mutual TLS exchange fails, and we don't even get as far as posting or trying to fuzz an API or anything like this. So, using this API, applications, libraries, and tools can retrieve credentials that identify them automatically without needing any secrets co-deployed. A SPIFFE ID looks like this, and it's encoded into an X.509 certificate, just like we saw earlier, using certificate extensions to encode further information. And because I know you love standards documents, this is where we are, the extensions down here in the standard X.509 ref spec. So how do we know that we can trust it? exactly the same way as before, certificate path validation, which is this slide, and chain of trust. This is broadly how SPIFFE requests an ID, and the attestation is the process of guaranteeing this metadata about an entity. So, we can see how further selectors can also be used to identify further workloads. SPIFFE is not a Kubernetes native technology. It is Kubernetes native, but it's not coupled to Kubernetes. It can be used anywhere that we need the bootstrap identity and used to identify all sorts of workloads. And here are the workload and node attester plugins that we use to bootstrap the identity process, specifically, again, inspire the reference implementation. It should be noted that this doesn't do any RBAC, it doesn't do any encryption, it is just the process of identifying a workload. This is the same as when we use a credit card to buy our certificate from a public TLS vendor, but it's just the difficulty of bootstrapping that workload and the elegance of the fix that makes SPIFFE so revolutionary. Now, when we use SPIFFE in Istio, we get free mutual TLS. And I won't go into too much detail here, but again, we have the subject alternate name of the certificate defined by the SPIFFE ID. We use the magic of Envoy, which is all things to all men, the mother of all proxies at this stage. And Envoy has a persistent HTTP2 mesh connection to every other Envoy instance. And so it's able to proxy the outbound request from the front end. There's a mutual TLS handshake at point 1 there, where they both identify each other using the TLS certificates encoded with the SPIFFE IDs that we've bootstrapped the network with. The discovery service of Envoy is beyond the scope of this ever so slightly, and in fact, we don't really care about the mix either, but we do get secure data transmission between our components. We get this for free, we get this securely, and we get this at scale. So, a bit of a recap. End-to-end encryption, private, mutually trusted communication between the API server and its callers, and encryption for the values in our etcd store. What do we have here? End-to-end encryption for the API server, giving us a baseline of trust between all the Kubernetes components. SPIFFE to identify the application workload so that we can then bootstrap the certificate signing process to get those mutual TLS certificates. In Istio's case, Istio runs its own certificate authority. Again, it's a root CA. It's distributing that trust bundle amongst the workloads so that everybody trusts that CA, because we're within our own trust domain. And then we have the certificates issued. And then finally, Envoy acts as the free distributed systems library sidecar, sitting outside of our application code and performing all these advanced encryption and routing features for us almost for free. So, what are we going to take away from this? Do encryption. It's great. And while you're there, you may as well encrypt everything. And for every concern that you possibly have, please do encrypt it. So the conclusions here. Network security is super important. There's no point running very well-tightened, process-bound security primitives if we then leak information on our networks. These old technologies and constantly updated cryptographic TLS ciphers and standards keep us secure, and they do so in much the same way online as they do in our trust boundaries of Kubernetes. Cloud-native applications have more security primitives. There is a much wider attack surface exposed by the complexity of Kubernetes, so we do need to run automatic test workloads, continuous security, constant verification that what we put in place yesterday is also in place tomorrow, and that any changes as we ship features do not impact the baseline security of our systems. Istio and SPIFFE give you wings, and please encrypt everything everywhere. Thank you very much.